And I want to thank the organizers for inviting me. And so this possibility is to join the celebration. So what yesterday I was trying to remember when I met Sasha for the first time, and now that I definitely remember this, that was a conference in Chernogolovka. And we actually, no, of course, I knew Sasha because we were from the same department. I was a PhD student. Sasha was a lecturer at that time. And conference in Chernogolovka, and kind of it's hard to believe, but no Google Maps, no internet, no computer. So you need someone just to show you the way to this institute. That was Sasha. Sasha was my kind of, I would say, my guide, first guide, maybe to kind of to the uh, world of integrability in broad sense, because I was working in my small group, and that time didn't understand anything about this. And since then, Sasha helped me and supported me in very many ways. And yeah, thank you, Sasha. And the second thing, also, I remember the first paper by Sasha I read. That was two remarks on the connection of Jacobi and Neumann integrable systems. And that paper was about kind of interesting phenomenon. And when you have two integrable systems, and so there is a map sending the trajectories of one system to trajectories to the other with the change of parameterization, and that's exactly the same phenomenon I'm going to talk about today. So geodesically equivalent matrix and Nijenhuis geometry. When I was kind of preparing so this talk, what I have in mind, so this is a very classical subject, geodesically equivalent matrix. But if, for instance, if I want to give a lecture course on this topic now, then so how would I do it now? And now to my explanation, almost all of them would based on the notion of Nijenhuis operators. And then so what I'm going to kind of do now, it's kind of imitate this course. And so we will start with the definition, of course, definition of Nijenhuis operator first. So what it is, so that is it's a very classical object now. So this is a tensor field of endomorphisms satisfying so one condition, so the Nijenhuis torsion must vanish. So this expression here, so is it's a formula to Nijenhuis torsion introduced by Nijenhuis in 1951. That, or maybe even a little bit earlier, so that was his PhD thesis. So if you are not happy with this very short formula, that is the next is just more naive understanding of this object. So this is a matrix so whose entries depend on the local coordinates x1, xn, and these entries satisfy huge system of nonlinear PD. However, so it's a kind of very good PD, so it's linear in terms of variables. And it kind of, it looks like Jacobi identity for Poisson structure a little bit. So next, so we need, just if you have never heard about Nijenhuis operators, we need some examples. The first example, you just take a matrix with constant entries. Of course, it's a Nijenhuis operator because derivatives vanish, and it's obvious. So next example, take identity operator and to multiply it with any function. So it's just scalar operator. It's also Nijenhuis. It's easy and follows immediately. So the next that is the first application, I guess, of this idea in Nijenhuis torsion. Complex structure. It's a very famous theorem by Newlander. Nirenberg says that so if you have an almost complex structure, an operator whose square equals minus identity, then it's going to be genuine complex structure. So if and only if this is Nijenhuis operator. So the next the series of examples that I wrote them these operators in this form, and I thought that it's kind of beautiful. So the first one, it's so the diagonal operator with entries x1, xn, and this is not just an example. In fact, if you have a Nijenhuis operator with the real eigenvalues, and you assume that these eigenvalues as functions are independent, you can always reduce it to this form. So the next example, so what it is about. So you take a Nijenhuis operator and you consider the coefficients of the characteristic polynomial. So these are exactly, so if you remember linear algebra, that this matrix is known as companion matrix, exactly these guys. So now, if you assume that the coefficients of the characteristic polynomial are independent, these functions functionally independent, then you can reduce this matrix to this form. And finally, so if you have an operator which is algebraically Jordan block with non-constant eigenvalue in the sense that the differential of this eigenvalue is not zero. So then you will be able to reduce to this form, and somehow, and you cannot make it simpler. So that is the simplest possibility. So in the next example, take an operator constructed by means of this formula. So what is this S? No, it's again, so it's companion matrix. So these are coefficients of characteristic polynomial. So you need to do something with this matrix to get a Nijenhuis operator. You need to multiply on the left and on the right. It's some similarity transformed by means of Jacobi matrix. Jacobi matrix for just for these functions.
These are elementary symmetric function of
element. Of eigenvalues. Yes. Of course. Yeah.
But x, you have x. X is x1, xn.
So here x1, xn. The idea is, so here x1, xn, you choose a very special coordinate system.
Yes.
So here you take just arbitrary coordinate system. In this arbitrary coordinate system, you compute the coefficients of the characteristic polynomial, and in terms of x, so they are not polynomials.
I see.
Not at all. It could be anything.
It's not symmetric. It's not symmetric function.
Not symmetric in terms of x. No, not at all. No.
It's
just
coefficient of characteristic polynomial.
So these are. So this formula is universal. And so one more example, which will appear later. You take Rn and consider operators constructed by means of this formula. So A is a symmetric matrix, B and X are column vectors. So this is matrix of rank 1. So you make it symmetric, and here also matrix of rank 1 with K. So this K, K is a constant, which
no.
K is a constant. It's scalar, which somehow is the curvature of certain metric. A is just constant symmetric
matrix.
Yeah. So it's the capital is a little bit confusing maybe. So these are examples. So Nijenhuis operators. So if you consider just this operator as it is, you need some sort of partners for this operator to make things more interesting. And the next definition, it's before the definition. So just so the one fundamental property, I believe. This formula, I find it very beautiful, but it is extremely useful in the theory of Nijenhuis operators. So take characteristic polynomial, consider the coefficients of the characteristic polynomial as functions, and then what you want to do, you want to understand the properties of the differential of the characteristic polynomial, and then this very nice formula holes. So that the differential of the characteristic polynomials is kind of related to the differential of just a trace of this operator. And this formula
What is star? It's
star, it's a star means I think of this operator as operator acting on vectors, and star it's just action on covectors. So if you remove, you need to just take differential as a row vector and multiply on the left or. And also the other interesting fact, if this condition holds true and the coefficients of the characteristic polynomial are independent, so then this is characteristic property of Nijenhuis operator. So if it is true, then the operator L is Nijenhuis. So the next, something. So what we call conservation laws and symmetries related to operators, not necessarily Nijenhuis operators. That I will give so these definitions and then explain so what is that. So the function f, just smooth function, so that we will refer to it as a conservation law for an operator. If so this condition holds here, you take differential of f, apply operator, and the form you obtain is still closed. I should use the different terminology here. That's that I should say is this is density of conservation law, but in the context of Nijenhuis operators, density not clear what it is, but so let's use this terminology. And symmetry. What is a symmetry? It's a symmetry of an operator or field of endomorphism is just another operator, so satisfying two properties, so they commute algebraically, and also this expression here so should vanish for any vector field xi. Of course, both definitions come from the theory of evolutionary systems. So to each operator you can assign evolutionary so PDEs of hydrodynamic type, and then the F is exactly the density of conservation law in classical sense, and so symmetry means that these two evolutionary flows commute, so symmetries of each other in the sense of PDEs, and also that I will introduce so the one more property, so the one more kind of symmetry, strong symmetry, so that will require, so it kind of, this is the same expression, but where xi and xi, not xi, but xi eta. So this is quadratic form, and I want to use bilinear form. So then I should write it in this way. And this property, so this formula is also was introduced. This bracket was introduced by Nijenhuis for two operators, commuting operators. If A and B commute, so this expression is a good tensor operator. And also, so I want to
Strong
say
symmetry means that it's stronger than.
it's stronger because so this
Yeah,
is
yeah,
if
but
you
I mean,
substitute
the meaning of
if you
this?
take psi, you will get exactly this.
What's the meaning of strong symmetry?
No, to me, no, meaning in that sense, in the
yes,
sense of the PDs, I don't know. No, it's and we obviously will criticized already many times for using this terminology. So there is no relation, but no, it is strong because no, it's stronger than this. But on the other hand, in terms of operators, also this is it's this relation is even more natural than this.
saying that L is Nijenhuis is equivalent to saying that it's a strong symmetry with itself. Is that correct?
Yeah, that's correct. Yeah, exactly. Yeah. That is the same. And one more property of Nijenhuis operators, which I guess this property is many of you are familiar with this. You take a conservation law, and so then each conservation law for the Nijenhuis operator generates a hierarchy of conservation laws. So this is that is property is well known for recursion operators, and so that's what Franco explained so many years ago. So how to use recursion operators to generate integrals of integrable systems. But I just want to emphasize that this is just a property of this operator L doesn't need to be recursion operator, just any Nijenhuis operator. It works, and also this property is characteristic again, because if you take arbitrary operator which generates such an hierarchy, and so the differentials of the functions obtained are linearly independent, this operator is Nijenhuis. So the if and only if.
What's the difference between recursion and Nijenhuis? Because recursion, so Nijenhuis not necessarily recursion.
No, it's just any Nijenhuis operator so satisfies this property, and this is it's not kind of theorem. It's just interpretation of the definition. It's you don't need to prove anything. Just look at the definition and interpret this definition in terms of
This is a conservation law of a sum equation, and you have because usually we have in recursion operator we associate recursion operator with equation, and then we generate things.
Sasha, this equation, there is no Hamiltonian structure here, Sasha.
So you have some equation and you have some Nijenhuis operator not related to this equation.
Look, Sasha, so this the point of this sort of how to say it, context, let's say that. So let's forget about integrable system. So what I say that Nijenhuis operators are not just interesting on their own, and forget about their relation with integrable systems, and so today so there will be no integrable systems in this sense at all, but I want to explain that Nijenhuis operator is still very helpful.
It's kind of not generalization of symplectic structure, but rather complex structure. Nijenhuis, is it correct?
No,
I mean, the complex structure is
to me, so to me, Nijenhuis operators are no. First of all, maybe to start with, you have an operator, just field of endomorphism, and you want to say that, so it's just too general if you do not impose any.
But what's the meaning of Nijenhuis
Conservation
equal to
law.
0? It's what was for Nijenhuis this?
What is the reason?
Yes.
No, theoretically, so this is just it's I want to explain this. This is kind of the only condition you can impose on a field of endomorphism, the simplest one, differential condition. You cannot write down anything else, but what he did,
Integrability of eigen.
the problem he was trying to solve was exactly this. You have an operator, you consider eigenvectors, so they generate distribution, and you want to know when this distribution is integral. The final answer is it's not Nijenhuis but Nijenhuis, but first discovery was this. Okay, the symmetries in the simplest case. If my operator is just diagonal, Nijenhuis operator is diagonal with different eigenvalues, So then that should be xn here. So then the conservation laws are trivial, so they're just functions of this kind, and the symmetries also are very easy to describe. And so there is nothing interesting here, so, and maybe for this reason, to pay attention to kind of to this sort of phenomenon. But what I want to say that this should be clear from the very beginning, I guess. Now, for me, L, if L is diagonals, and then so the whole story is very simple and classical. It's not
Mn
interesting.
of xn.
Yeah, so it's xn, of course.
Is I, are they the same as X or
Hmm?
as U?
Oh, sorry.
Should be
So
X.
it should be X.
Should be X, yeah.
Sorry. So it's U1, UN here.
U1, UN.
Yeah.
But my point is,
Riemann invariance in terms of this, right?
Riemann invariance, of course. So that's when you say that. So there, you consider semi-Hamiltonian system, and Riemann invariance. Basically, you want to say that there is some Nijenhuis operator
don't need
behind.
Hamiltonian structure.
Yeah, we don't need Hamiltonian.
That's what you did.
So it's what I was going to say, that these operators are not necessarily diagonalizable. And what is much more important for us, so we want to treat the situation when eigenvalues may collide. And then so this this kind of singular points, so they are not covered by this theory, and you need to something else. But the point is still that everything which you can observe in this situation, like the conservation law is defined by n functions of one variable each, and the same for the symmetry. So this is still true for all Nijenhuis operators, even at singular point under one regularity condition. So you assume that powers of this operator are linearly independent. It means that you're happy with collisions of eigenvalues, but so when they collide, Jordan block appears. Just one Jordan.
Linearly independent over what? Over what? Linearly independent.
Every point.
So these are matrices. They are independent as matrices.
Space of coefficients.
Space of matrices.
Every point.
At every point. Yeah, so this is algebraic.
Constant is constant.
So next, and so then it follows from this that if you take this operator L as if you consider system of hydrodynamic type, so then it is of course integrable, and there is nothing interesting to discuss. But you can use these operators to generate non Nijenhuis examples of the integrable PDs, and you can do it in this way. So that's another formula I like. Take Nijenhuis operator and consider an operator just obtained in the constructed findings of this formula. What is written here? So this is what is called Edgergate matrix for L plus L minus lambda. So this it is in terms of lambda, lambda is a polynomial of degree n minus 1. So then the statement is all these operators symmetries of each other. And so these functions as one divided by the characteristic polynomial. So these are common conservation laws for all of them. So they generate the very nice, beautiful, and very helpful so integrable system of hydrodynamic type. This is not, I have to say immediately that it's not our invention. So this is, this case is in the intersection of two theories developed by Zhenya, weakly nonlinear semi-Hamiltonian system. So this is one of examples. And also, so what Franco and Paolo Lorenzoni did some cohomological construction of hierarchy of integrable system of heterodynamic type. So it's if you you get exactly what you did if you take a Taylor expansion of in lambda at infinity, so that you will get exactly your construction here. So the one more thing, one more formula which I like. Is how just another method so how we can describe common conservation laws. Take any symmetry for L. So this is a matrix operator which commutes with L, and therefore so can be written as linear combination of powers of L. So then take coefficients of this linear combination. The first of them will be common conservation law for all these operators, and that's what it means. It means that you apply this operator and you will get a closed form, and this closed form just takes can be written in this way, and everything is very easy to prove for Nijenhuis case. So just one example of a proof. So if I want to check that the ratio 1 over characteristic polynomial is common conservation law, that's just a one line proof. I don't want to explain this, just one line. It's absolutely straightforward. And now the next topic, I only have 15 minutes for it, sorry. The geodesic flows.
A couple, list a
Okay,
couple.
yeah. Okay.
We were late.
So to the geodesic flows, you have a metric. So geodesics are the locally shortest lines. So I've stolen this picture from Wikipedia. It's a geodesics on the ellipsoid. So very nice. And so what we're going to discuss is maybe I will use another illustration from Wikipedia. So these are how the traces of flights from Heathrow. And if you look at this map, they are not straight lines, no, but they're still shortest in the sense of the round sphere. And then you can ask the following question. So can you make a geographic map such that so all these spaces are straight lines? Can you do it or not? And that is exactly a question about geodesic equivalence. The main definition is as follows. So you have two Riemannian metrics. They are geodesically equivalent if they have the same geodesics if you ignore parameterization. The trivial example, of course, if you take two proportional metrics with constant coefficient of proportionality, then nothing changes. And the other example, which answers to the question I just asked, is this. You take a sphere and you take the central projection to the plane, and then of course every equator becomes a straight line, and this shows that the geographic map so can be constructed if you assume that the shape of the Earth is just a round sphere. But if you remember that it's not a sphere but like an ellipsoid, then such map does not exist. And the problem asked by Beltrami long ago was to classify all pairs of equivalent metrics. So this is a very rigid condition. Not every metric admits geodesically equivalent partners. So then this question was asked, and the answer was obtained almost immediately. So by Levich-Witt, he wrote this formula here. So it says that if you take the Riemannian metrics and you assume that the point is generic, non-singular, so eigenvalues of what? So you have two quadratic forms, and there is an operator between them. So if all eigenvalues are different, then So this is canonical form for so G and G bar, and it looks like everything is done, but not quite. No, first of all, absolutely unclear what to do in the case of pseudo-Riemannian matrix, which is also interesting for many reasons. And what happens at singular points, when where the eigenvalues of the separators collide, and then without Nijenhuis geometry, I'm afraid nothing can be done. Okay, so where is Nijenhuis separator here? Nijenhuis separator, so as I said, so there is a very natural operator to which establishes the relation between these two quadratic forms. So that's that I wrote in a matrix way, but you need to use some sort of strange normalization here. So if you construct operator by means of this formula, so then you will get something interesting. And this formula is maybe is not very nice. It's much better to write this formula. So the relation between this operator and these two Geodesically equivalent matrix in this way. And why it is nice? And this is an observation by Sinyukov that long ago. So if you rewrite the condition that G and G bar so have the same geodesics in terms of this operator L, so then this equation becomes linear. It's a linear PDs in terms of L, and then the L is kind of is an object which should be used in this theory. So the conclusion is that if you want to study so G and G bar, so then maybe it's better to study L and G, because G bar so can be reconstructed, and you want to study pairs L and G, so satisfying this condition, and that's exactly what Franco did in the case of Nijenhuis Poisson manifolds. And instead of studying two compatible Poisson structures, it is more convenient to study Poisson structure plus operator, and that's exactly what we are going to do here. Okay, so then we have an operator, and so what about the properties of this L? And of course, the main fact is that this is Nijenhuis operator. This operator is Nijenhuis, and as soon as you observe so this property, so then you want to do something, you want to use this property, and the first thing is to construct first integrals, so killing tensors starting from the separator L, and surprise surprise, so this is exactly the killing tensors are exactly the operators that we discussed previously. Weakly nonlinear semi-Hamiltonian systems, or the homological constructions suggested by Franco. These are very nice objects, and so they commute in terms of the standard Poisson structure on the cotangent bundle. And if my operator is regular, so then they are functionally independent, and you get integrability of geodesic flow in the classical sense.
It means that the following is equivalent, or
What's again?
Theorem is that those things are equivalent, or it's just a set. He's asking.
No, these are
Separate list of
no, that's not equivalent. So this if G and L are related as explained, so then so 1, 2, 3, 4, 5. Not
killing tensor means just invariant under
killing
maybe
tensor. Killing tensor means that you if you like this, I like this definition. So I say that this operator is killing tensor if this function is first integral function defined by this operator. So what the why so this why that I like this because the proofs. What I remember. I have to say that you see, so there are many authors. So here mentioned because these properties were discovered by independently by Serezha Tabachnikov, Matveev, Topalov, and the problem was to prove that they come. But now it is just for free because the model that's above discussion. So then these operators are symmetries to each other because it's a very interesting fact. So if you have two quadratic integrals of certain geodesic flows and you consider the corresponding operators, you assume that these operators commute algebraically, and then they Poisson commute if and only if so these the corresponding evolutionary flows commute. So that's kind of it's natural fact, but I don't know if no.
Here's momentum, so they're all quadratic. Here's momentum, so that they're all quadratic.
Yeah. So this has the property of quadratic integrals. Okay, good. But now, so the one more question. You have an integrable system, integrable geodetic flow. You want to add potential, and in such a way that the system remains integrable. So how to do it? Again, so you have already seen this formula. You take symmetry of L. You consider linear combination of powers of L, and you just take the first coefficient, and this first coefficient is exactly the potential you need. So then the new integrals so it will be defined in a very simple way, and then this is how conservation laws occur in the context of just classical integrable systems. And then the fact that these guys should be at conservation law, it's a kind of trivial observation in this context. Okay, what next? The metrics with whose geodesics are straight lines. So how to describe them on the plane or in Rn? How? No, so you take this matrix and you are interested in all matrix G bar. So to having the same geodesics, you take this Sinyukov equations. You are not looking for G bar, you're looking for L. And these equations look, if G is flat, then it's quite simple equations, the PDs with linear, with constant coefficients, you immediately solve it. And when you solve it, you will get exactly this operator, which was one of my examples. And then the theorems is just like this. All the metrics, so having straight lines as geodesics, so they define by this very simple form, where L is explicitly given here.
Curvature is constant here.
Curvature will be constant. By the way, I didn't mention this. That was one of theorems proved by the Beltrami and Schur long ago. So and they proved they didn't know this formula, but they proved that so if you have a matrix whose geodesic lines are straight lines, so any parameterization, the curvature must be constant. Okay, so now next question. So do we ask ourselves is the following: so take an operator L. No, assume that this is good operator. So yeah, okay. So then, so what you want to do? You want to find a partner metric which is geodesically compatible to it. So how to do it? No, but then there is something magical here. So if this operator is the regulars, then you can always find coordinate system such that the matrix of this operator takes this form. It's also companion form, but so the coefficients of the characteristic polynomials are here in that last row, not the first column, but you can do it. Then, so in this coordinate system, the metric is like this. It's very beautiful again. So you take here's the coefficients of the characteristic polynomial. So it's once here, and the statement is that this is explicit formula which for given GL regular operators so produces geodesically compatible metric. So everything is very explicit here.
It should be Nijenhuis, Nijenhuis.
Yeah, at least Nijenhuis, of course. No, if not, then nothing will work. No one, but this is so how you can solve the Beltrami problem. So what is important? There is something important here. This L is not necessarily diagonalizable. The L may have any algebraic type, collisions of eigenvalues. So this formula is still universal. So how to apply this formula? To find such a coordinate system where L has this form is difficult, and not maybe not difficult, but it's very unpleasant. So what you need to do, you need to just to make change of variables to write down the formula in the coordinate system you want. So L is given, and for instance, L is diagonal. So what to do in this case? No, but then you need to make change of variables. So there's a standard formula. So how the components of the metric transforms, and but you need to know what this C is, the transition metric. Transition metrics is very easy. You need to take conservation law, and then the first row will be this conservation law. There's a Jacobi matrix, so each row is a closed form. So then you apply L, and then you will get formula for G in any coordinate system. So if you have a good conservation law for this operator L, if you take a diagonal operator and apply this formula, it's just algebraic. As conservation law, you take just sum of x1, x2, x10. So you do this computation, and you will come to this result in the diagonal coordinate system. Your metric is like this, where so what is this? So sigma is a characteristic polynomial. You take different derivative with respect to lambda and substitute eigenvalue. And what is this? This is exactly the Levi-Civita formula. Just the kind of no mystery, but just short version of it. I have 1 minute. Do I have 1 minute? So the next, what I want to say, so this is so basically what I'm trying to explain now. This is how we can interpret classical results by using this operator L. But so what is nice that if you use this formula for L not diagonalizable, so having Jordan blocks, you will immediately get classification or analog of Levi-Civita formula for pseudo-Riemannian metrics, and that was the long-standing problem for 100 years, and by using Nijenhuis operator, that was completely solved. But so what is still unclear? So what happens at singular points where eigenvalues collide? If you know what happens to the Nijenhuis operators, well, then you using this kind of magic formula, you can describe G, and then I will have to skip a few slides and just to say that. So what the last result, which in my opinion would not be possible to get without Nijenhuis geometry, it's complete description of all singular points for the geodesically equivalent metrics in dimension 2. It's a very long list, So this is just an example of two formulas with G and Del, so how they look like. It's not easier. No, but if you know that if you can classify Nijenhuis operators, so then you will be able to reconstruct G. And now that the Beltrami problem, at least in dimension 2, is completely solved, which would not be possible without this knowledge. So there's some references and happy birthday, Sasha. Thanks for
We had quite a lot of questions during the talk. Has anyone got one quick question?